Hello, Sauce here. This is a AP Calculus video lesson on investigating change. This lesson is more of an introduction to concept lesson rather than a example of how to do a type of problem. This investigation is going to introduce many interrelated concepts. And the concepts that I'm going to show you and how they're interrelated are essential to understanding many things that we are going to do in calculus moving forward. It's good that this is a video lesson because it would be a common experience for somebody that is new to these concepts to get overwhelmed by the pace at which I'm going to talk about the details of these concepts. So if you're getting overwhelmed, it's a very good idea to stop the video, think about what's being said, and maybe rescan it. The more that you can get from this initial presentation, the better, because we're going to continue to use these concepts and it'll be very clear in the future what's being talked about, the more that you can understand here and now. So we're going to investigate change. And what we're going to investigate is a simple function that I'm going to define here. The f function is x squared, parent quadratic, very simple parabola. And how we're going to investigate it is we're going to make a table of values. We're going to choose a domain for x and then find the values of f and look at the graph. The domain is going to be from -3 to 3. The integer values between -3 and 3 I'm listing here. And we'll make a column for the values of the f function. When I put -3 into the function, I square it and I get a +9. And I can continue to fill up the column for f fairly quickly. -1 squared is 1, 0, 1, 4, and then 9. We can see that there is symmetry in the values of the table because there is symmetry in the graph of x squared. We're familiar with the graph of parent quadratic. It's a parabola whose vertex is at the origin, the point 0, 0. And if I continue to graph these points, I can plot them like this very quickly, where this is 4. The point -3, 9 is a little off my graph, or what I've chosen to present here. That's okay. I'm going to connect the points that I can see with that familiar parabolic curve. And I can investigate the change in my graph. I can see that the values of the function at the beginning of my chosen interval are fairly high, and as x increases from this negative value in the domain, the values of the function decrease. They go down until I get to this turning point at 0, the origin, and then the values of the function change by going up. So a simple observation of change in this function is that the values decrease here and then increase afterwards. I can be more precise about how the values of the function are changing by making a column and calling it delta f. Delta is the symbol for the concept change in, so delta f means change in f. And I can enumerate or evaluate that change. From the point or the value 9, the function must change by decreasing by 5 to get to the value 4. So between these 2 points, I have changed -5. And I can do that. I can list the amount of change between any 2 consecutive points in my table that I've chosen by putting the value of the change, in this case from 4 to 1, I have to decrease by 3. I'm putting that change in between these 2 points. I can continue to fill up this column. The change from 1 to 0 is a change of -1. We have to decrease by 1. But then we're increasing. From 0 to 1 is a positive increase, a change of 1. And then we have a change of 3. And we have to go up by 5 to go from 4 to 9. That's the change. Now, calculating the change was easy to do by observing the table values. I want to remind you that this change is also the concept of average rate of change that we've studied in previous lessons. Quick review of average rate of change. The average rate of change is the slope of the line that connects the 2 points that you're investigating the change between. For example, here, if I go from the point -2, 4, right there I'll highlight, to the point -1, 1, I've highlighted there, the change of -3 is also the slope of the line that connects those 2 points. And the slope of the line that connects any 2 points on a graph is called the average rate of change. It's a slope calculation. In this case, we could think of the points having a rise and a run. The run is 1 and the rise goes down, so it's a -3. The slope between these 2 points is a -3 over 1, or simplified to -3. We can investigate change even further. We can think of, if we can think of delta F itself as being a column that lists the change in F, then we can make another column which investigates the change in delta F. Symbolically, we could say we're investigating the change in delta of the change in F. Delta, delta F. And let's do that just as we did before. If delta F has a value of -5, that then becomes -3, how did it change? Well, we had to change by 2 to go from -5 to -3. And what do we have to add to -3 to get to -1? 2. Again, a change of 2. And if we keep going, we change the values of delta F by adding 2 each time. Which is curious because the column delta delta F, which is the change in F, we observe that it is constant. We have a constant delta delta F. What kind of information is delta F? If we can observe very easily that this column is a constant function, constant change of 2, then what kind of function is represents delta F? Well, observe that these values have a constant rate of change of 2. I've already discovered that here. But what kind of function in mathematics has a constant rate of change? A line. And the line that represents delta F has a slope of 2. It's constant change. I graphed F as the parabola. I can also graph delta F as its own function. Delta F's graph is going to be a line with a slope of 2. I can label this line delta F. It's a linear function. And the values of this line are in the table here. This parabola I can label as F. And if I've graphed F and delta F, I can also graph delta delta F, which is going to be the constant function 2. Horizontal line, constant function. I'm going to label that delta delta F. We have 3 functions. They're interrelated. I've got the parabola, the change in that parabola, which is the line, and the change in that line, which is this constant function. Let's talk about these functions being in a real-world context. Very often, functions that we use in science are functions for the position of an object. We could imagine that this parabola, the quadratic function f, is a position function. Position of what? Well, anything. Maybe a car traveling on a road. If we are on the position function, then anywhere that we can be on it needs to be relative to some initial position at an initial time. The origin represents then maybe our starting point or home, and we are in the car traveling away from home. So to be here on the f function, which is a position function, let's think. We are a distance from home. Home is the distance of 0, value of 0. And we have a high value here, which represents a distance from home, our position relative to home. And as we decrease our position, we are heading towards home. We travel along this function, and the values of the function decrease. We're getting closer and closer to home. And at some point, maybe time 0, then we're at home because we're at the origin with a value of 0, 0 distance from home. And then as time moves on, maybe into the future, we are traveling away from the home as the values of the position function increase. That reality is captured in the table. It's captured in the graph. So if we think of f as a position function, what does delta f mean? What kind of function is the rate of change of position? We're in a car, and that car is traveling towards home, and the rate at which we are traveling is our velocity. Delta f, if f is a position function, is a velocity function, because velocity is the rate of change of position. A car is a machine that changes our position, and the velocity of the car is the rate at which our position is changing. Notice that the velocity itself is changing. We're going at a different velocity at different times. That's captured by the curvature of our position function. Let's investigate that. If we are on the position function here, where I'm holding my pencil, then the rate at which we are traveling home is more intense. We're going faster towards home, much more quickly here, than if we were very close to home. When we're close to the origin, then the rate of change is slower, less slope. And the further we get away from home on the graph, then the more intense our velocity, the steeper our slope. It's captured in the table values, and we can see it in the curvature of the position graph. If delta f is a velocity function, and we graphed delta f right here as a line, the line captures that same interrelated concept. If I put my pencil on the velocity function here, delta f, the line, that is a negative value, and it's a more intense negative value than something closer to the origin. This negative value here means that, well, it's negative. That means that I am going towards home. I'm lessening my distance. And the rate at which I'm lessening my distance is more intense the further away I am from home. And then the line, when it goes into the positive region, it means that my velocity is positive. That means that I'm heading away from home because I am increasing my distance. And the further away I get from home, the faster my rate of change of distance, the faster my velocity. And we can see that the values of the velocity, literally the values of the line, are themselves increasing. We go up the line, we have higher values on the line, that's a higher velocity. Lastly, if velocity is the rate of change of position, then what is the concept of the rate of change of velocity? Delta delta F, the rate of change of velocity. We call that acceleration. And to get this concept, we could imagine ourselves being in a car. If we are traveling down the highway at 40 miles per hour, and we are going at that constant 40 mile per hour velocity, we're not changing our velocity. Our position is changing at the rate of 40 miles per hour. But if we're constantly going 40 miles per hour, our velocity is not changing. So what do we do to go 50 miles per hour? We step on the gas, we accelerate. Acceleration is the change in velocity. And if we are to step on the brake, we would decrease our velocity. We would decelerate. Or we could think of going from 40 miles an hour and slowing down to 30 miles an hour as a negative acceleration. So what does that have to do with our presentation here? Delta delta F has been graphed. It is the constant function 2. And we're now thinking of this as an acceleration function. Our velocity is constantly increasing at a rate of 2. It's also the line's slope. Last thing to notice in this presentation is there is a relationship between position, velocity, and acceleration, conceptually, that we've been talking about. What about the relationship of these three functions, purely observing the type of function that they are? The position function is quadratic, a square. The rate of change is the line, which is reducing the exponential value from 2 to 1. And the rate of change of that line is the constant function, which can be thought of as reducing the exponential value of 1 to 0. There is absolutely a purely mathematical relationship between the types of functions that represent this conceptual relationship. And we're going to investigate all these subtleties and interrelated concepts quite a bit moving forward.